Imagine a boundless black ocean, where instead of waves there are currents of incandescent gas, and instead of beaches, an endless horizon of cosmic dust. It is in this setting that new solar systems are born, in a dance of matter and gravity that, if we could watch it in fast motion, would resemble a hypnotic whirl of light and shadow. But the birth of a planetary system is never a silent event. It is a primordial battle, where the gravitational pull of a young star tries to seize the surrounding matter, while jets of plasma and stellar winds push away what it cannot engulf. These young stars are known as accreting stars, and they represent a crucial stage in the life of a newly formed star. At this phase, the star is wrapped in a protoplanetary disk, an immense ring of gas and dust, remnants of the molecular cloud from which the star was born. Within this disk, tiny particles collide and merge, giving rise to increasingly larger bodies until they form protoplanets. The gravity of the star and the instabilities within the disk shape these formations in a process that can last millions of years. The star, however, does not simply remain still at the center of this cosmic carousel. Through a complex mechanism, matter from the disk falls toward its surface, following magnetic field lines as if they were invisible rails. When the material plunges onto the star, it releases enormous energy, heating the surface and producing intense luminous emissions. At times, the accretion can become so violent that it generates true bursts of brightness, visible even from great distances. One of the most fascinating aspects is that these events are not constant. Astronomers have observed young stars transition from relatively calm phases to periods of explosive accretion, during which the mass accumulated in just a few weeks can equal that of several Earth-like planets. This suggests that the evolution of a solar system is anything but linear. There are moments of calm, followed by periods of chaos in which the entire forming architecture can be overturned. In recent years, thanks to instruments like ALMA, Atacama Large Millimeter, Submillimeter Array, and the James Webb Space Telescope, we have been able to observe with unprecedented precision the details of these protoplanetary disks. Some display incredibly ordered structures, with rings and gaps that seem sculpted by invisible hands. Others, instead, appear as turbulent vortices, signs that planetary formation is still in its infancy or that gravitational interactions are shaking the entire system. In some cases, the gaps in the rings coincide with the orbits of already formed planets, which, like cosmic plows, push away the disk material and leave behind empty trails. And yet, the most surprising element of these observations is that there is no single model. Some systems seem to be born in order, others in total disorder. This could explain why the universe hosts such a variety of planetary architectures, from compact systems with planets larger than Jupiter orbiting closer than Mercury, to systems similar to ours, where small rocky planets inhabit the inner zones and giant gas planets keep watch farther out. But what happens when the star cannot control all the surrounding matter? In some cases, the gravitational competition between nearby stars can steal parts of the disk, or, in more extreme scenarios, lead to the birth of binary or multiple star systems, where two or more stars share the same cosmic cradle. These configurations, far from rare, give rise to complex and often unstable planetary orbits, where planets can be ejected into interstellar space or forced into elliptical trajectories that periodically bring them very close to their parent star. It is a process where violence and creation coexist, a fragile balance between forces that can both build and destroy. And it is precisely in this borderline zone between stability and chaos that the fate of a nascent solar system is often decided, for the future of these systems depends not only on the star and its ability to accrete matter, but also on the chemistry and internal dynamics of the disk. By analyzing the light emitted from these regions, astronomers have discovered the presence of complex molecules, including precursors to amino acids. This means that the recipe for life could already be written in the first millions of years of a system's formation, long before a planet with oceans and atmospheres can emerge. The discovery is fascinating, Many of these molecules form in the extreme cold of molecular clouds, long before the star is born, and survive the chaos of accretion, remaining trapped in the material that will go on to make up planets, moons, and comets. If this is true, life may not be a rare phenomenon, but a potential common outcome of planetary formation, at least in terms of chemical ingredients. Observing accreting stars is not only a glimpse into the universe's past, but also a mirror in which we can catch a reflection of our own history. About 4.6 billion years ago, the Sun was also a young star, likely going through phases of violent accretion and instability. The comets in our system, with their primitive compositions, are like time capsules, frozen remnants of that chaotic period. By analyzing them, we are discovering that some of the water and organic molecules we find on Earth today may have arrived from those ancient fragments. But another question troubles astronomers. How many of these systems survive intact to maturity? Statistical studies suggest that a significant fraction of young planets are destroyed or ejected into interstellar space within the first 100 million years. This means the universe could be populated by billions of orphaned planets, worlds wandering in darkness without a parent star. Some of them might be rocky and Earth-like, yet condemned to a frozen, solitary existence. Meanwhile, the most active accreting stars display an almost pulsating behavior. Cycles of brightness and calm that could be the key to understanding how mass is distributed among forming planets. Some models suggest that during accretion peaks, the produced heat can push the snowline, the region of the disk where water transitions from gas to ice, farther away from the star. This temporary shift can determine the amount of water trapped in rocky planets, directly influencing their potential habitability. And yet, despite the power of our telescopes, we are still only at the beginning. Accreting stars are often shrouded in dust clouds that conceal their core, and every image we capture is just a fraction of the story. Each disk we observe is a unique snapshot, a single frame from a film that lasts millions of years. And if we could see it in its entirety, we would probably discover that the birth of a solar system is a far more variable and surprising process than we can imagine today. Perhaps, in some remote region of our galaxy, at this very moment, a star is completing its accretion and around it are forming blue planets, blazing deserts, gas giants, and icy moons. Perhaps one of those worlds will have oceans and clear skies, and millions of years later, someone, gazing at the night sky, will wonder how it all began. If you have made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.